Hello, everyone. This is the fifth talk of the year, and we have Dr. Bruce Bartlett today. He'll be talking on Hilbert's third problem and the geometry of tetrahedra. And his research speciality is topological quantum field theory, which is a subject at the intersection of mathematical physics and low-dimensional topology and category theory. So whatever all that means. Sounds very interesting. So yeah, Dr. Bruce, you can start whenever you're ready. Thank you so much for being here.
No, thank you, Rocco, for inviting me. It's a pleasure to give a talk to the society. And yeah, so I think you'll understand a bit more about what my research area is about through this talk, because you'll see aspects of it in the talk. So it all starts in 1900, where the world's most eminent mathematician at the time, David Hilbert, opened the International Congress of Mathematicians in Paris with a list of 23 mathematical problems for the new century. So he gave the opening address there. And there he is. And in his speech, we have this extract. Who of us would not be glad to lift the veil behind which the future lies hidden, to cast a glance at the next advances of our science and at the secrets of its development during future centuries? What particular goals will there be towards which the leading mathematical spirits of coming generations will strive? What new methods and new facts in the wide and rich field of mathematical thought will the new centuries disclose? So it was a very inspiring talk and reverberates through mathematics to this day. And here are his 23 problems which he gave at that talk. So this was the problems for the new century, the 20th century. And this is not, the language here is not the language that he used, but this is just a summary of it in slightly more modern language. And yeah, indeed, these problems really did shape mathematics in the 20th century. So it was quite an amazing achievement of Hilbert to have an intuition for what problems are really very interesting problems. And the one we're talking about today is this third one, the equality of the volumes of two tetrahedra of equal bases at equal altitudes. So that's not quite stated correctly as Hilbert stated it better, but you'll understand as we go on. Let's just have a look at a few other problems there. The first problem is Cantor's problem of the cardinal number of the continuum, which is a classic. I mean, that's the question of do there exist other cardinalities or sets between the cardinality of the natural numbers and the cardinality of the real line? And that was indeed a massive problem in 20th century maths. And eventually, the fact that there doesn't exist sets having cardinality strictly between those two was called the Continuum Hypothesis. And it was eventually proved that it's actually independent of the set theory axiom. So yeah, it was a huge deal. Yeah, we see the Riemann hypothesis in problem 8. Yeah, most of these problems were solved, and some of them still not solved, and some of them were a little bit vague. So it's not clear how to solve them. But yeah, they were amazing. And I also highly recommend this comic book, Logic Comics, by these two Greek authors who I struggle to pronounce their names, but incredibly creative guys. And they wrote a book in comic form about the life of Bertrand Russell, who was a mathematician / philosopher, and he was also very influential. And inside the book, there's a section where they go to the International Congress of Mathematicians in Paris. It was a very exciting time. I think the Eiffel Tower had just been built, and yeah, it was an amazing time around the world. So let's talk about the concept of scissors congruence in 2 dimensions. And then later on, we're going to go to 3 dimensions. So we say that 2 polygons P and P prime in the Euclidean plane are scissors congruent if they can be subdivided into finitely many polygonal pieces, such that each piece in P is congruent to exactly one piece in P prime. So here's a picture. This picture establishes that the triangle on the left, this big triangle, is scissors congruent to the square on the right. The reason being that you can chop up this triangle into 4 pieces, A, B, C, and D, And you can chop up the square into 4 pieces. And here we have a congruence between A, and B, C and C, and D. So you can chop up the triangle into finitely many pieces and rearrange those pieces to form the square. It's quite an intuitive concept, and that's called scissors congruence. And it's a theorem which was formally proved by Wallace and Johnson, but really probably due to the ancient Greeks and the Chinese, which is the following: that let P and P prime be 2 polygons in the Euclidean plane, then P is scissors congruent to P prime, if and only if the area of P is equal to the area of P prime. Okay, so let's prove this. So the forward direction is clear because suppose that P and P prime are scissors congruent. Then that means we can subdivide P and P prime into n pieces. So P1 up to Pn for P and P1 prime up to Pn prime for P prime. And clearly the area is additive when you subdivide. So the area of P is going to be the sum of the areas of the pieces of P, and the area of P prime is going to be the sum of the areas of the pieces of P prime. But by assumption, P is scissors congruent to P prime, so that means that P1 is congruent to P1 prime. So in particular, that means the area of P1 is equal to the area of P1 prime, and so on for all these little pieces. So each of these little areas are equal, so each of the terms here are equal in the sum. So that means the combined sum is equal, so that's therefore area of P is equal to area of P prime. Okay, that's a good warm-up. Maybe I'll just stop for 1 second here and just see if there's anyone with a question about what scissors congruence means. Maybe I'll go back to the slide, just so that you don't fall off the bus right in the beginning. Okay, so now let's try and prove the harder direction. Suppose that 2 polygons are scissors. So suppose that 2 polygons have the same area. Now I must prove that they are scissors congruent. In other words, that you can chop one up into finitely many pieces and rearrange it to get the other one. Okay, so this follows from the following lemma. Hopefully, if I push X, then this goes away. No, sorry. It will go away in time. So here's an interesting lemma, a lovely geometric lemma. It goes as follows. Every polygon P in the plane is scissors congruent to a rectangle with one side having length 1. Let's prove this. So the first step is that we can subdivide the polygon P into triangles. Basically just draw straight lines connecting all the vertices, and then that'll divide up P into triangles. Okay. Now each of those triangles is scissors congruent to a parallelogram by this diagram. I start with this red triangle, and then I can bisect these 2 edges with this line here, and then I could flip over this triangle and put it over here, and that would then create a parallelogram. So this shows that the red triangle, the original triangle, is scissors congruent to this parallelogram at the bottom. I hope this slideshow buttons go away soon. Okay. And carrying on, every parallelogram is scissors congruent to a rectangle. Because if you got this red parallelogram, you could drop perpendicular altitude from each vertex, and then that would convert you to this rectangle here. So I could move this triangle over to the other side, if you like. So the red parallelogram is scissors congruent to this rectangle over here. And now to end the proof, I need to show that every rectangle is scissors congruent to a rectangle with one side having length 1. So here's my original rectangle, this red one. And I want to show that it's scissors congruent to some other rectangle where one of the sides of that rectangle has length 1. Okay, so I don't care what this side length here is, AB, but let's suppose the original side length here is called H for height. And let's just mark off a length of one unit in our favorite units on this side. And yes, I am making some assumptions here. I'm making an assumption that H minus 1 is less than 1, just in the way that I'm going to draw my picture in a moment. If that's not the case, there's a perfectly analogous proof for the other case as well. Okay, so what do I do next? I take this little length here, H minus 1, and I extend CD by that amount. I don't understand why it keeps showing those slideshow buttons. So let me see if I oh well, I must just be patient. So, okay, so that's the first step. This creates this new rectangle over here. And then I draw a line from A down to the bottom right-hand corner here. I wish I could move this away. And that's going to intersect at points I and J. Okay, now I notice some angles are equal in this figure. So all these blue angles are equal. Basically, these angles here are alternating angles, and these angles are corresponding angles. So the blue angles are equal and the green angles are equal by elementary geometry. And that allows me to conclude that triangle AIE is congruent to triangle JHD by side angle side. Because you see they have two angles. I forgot this angle here, it's DHJ, is also a blue angle. It is congruent to the other blue angles. Okay, and they both have a side length of H minus 1. So by side angle side, those two triangles are congruent.
Should JD be H minus 1?
No. Dylan has confused me.
Yeah, if you look at the angles.
You're agreeing with Dylan, Leslie?
I think I am. Because the top one, H minus 1, is the length between, I'm assuming, the right angle and the green angle.
I think where I went wrong was that so say that again.
Or me?
Yes.
Maybe Dylan wants to. I don't know if the way I see it, H minus 1 is the length between the right angle and the green, not the blue, the green angle.
Yes, yeah. I admit to being confused. Sorry about that. I'm just going to power through, and we'll chat about this at the end.
Okay.
Okay. So the idea was that this is going to allow us to conclude. Therefore, this allows us to conclude that side AI is equal to side J, this side here. I can't remember what the bottom symbol is. So we've got an inequality of two lengths here, which then allows us to conclude that triangle ABJ is congruent to triangle IGH. Because we've got triangle ABJ and we've got triangle IGH. They have these two lengths, or they have this length IJ in common, and then they have AI, which is equal to J to the bottom vertex here. So that gives you a side that they have in common, and then they have two angles in common. Okay, so now let's have a look here. Rectangle ABCD is scissors congruent to the polygon CEIJD plus the polygon AIE plus the polygon ABJ. And the triangle AIE is congruent to JHD, as we just saw, and the triangle ABJ is congruent to IGH, as we just saw. So this shows that ABCD, our original rectangle, is scissors congruent to CEIJD plus AIE plus JHD plus IGH. And that gives us this rectangle on the bottom, which has got side length 1 and some other length here. Quite an elegant proof, right? Except I got confused at one point, but okay. So note that this lemma permits us to give a finite definition of the area of a planar polygon. Because we could now say that we could now define that the area of a planar polygon, P, is the side length x which occurs when we express P as being scissors congruent to some rectangle having side length 1. Because the rectangle on the right, its area is clearly x. So let me just stress that again. I could now give a new definition of area of polygon. I could say, take your polygon and find some other rectangle which is scissors congruent to it, which has one of its sides equal to 1. Then the length of the other side, that's what we define to be the area of your original polygon. Okay, so that's a finite definition because it involved finite many steps. And the question is, can we give a similar definition for the volume of a three-dimensional polyhedron by cutting it up into finitely many pieces? And this is the problem which Gauss mentions in a letter to Gerling in 1844. Okay, the point is that the ancient Greeks had found a formula for the volume of a pyramid, but it required the method of exhaustion, which was what Archimedes came up with. In modern language, we call that integration, which involves breaking it up into infinitely many pieces. Right? It's a limiting procedure. So the method for the volume of a pyramid, as you know, is if you know the volume or the area of the base, and you know the height of the pyramid, then the volume is just a third AH. So the Greeks had this formula. So they could calculate the volume of the pyramids in Egypt, for example. Now, how do you prove this formula, though? And the way that they proved it was by the method of exhaustion. And this is the issue that Gauss had. It seems like an elementary proof. You'd like to be able to prove it using finite mathematics. But let's just remind ourselves how the proof goes using calculus. We would slice up the pyramid into slices as shown, and the area of each slice at height y will be the area of the base times the proportionality constant. So as the area decreases to 0, as y goes from 0 to h, the area must decrease quadratically to 0 because area is a quadratic function of the lengths. So at height y, the area must be the original area times the ratio of y over h squared. So the volume of the pyramid is then the integral from 0 to h of the area of each slice times the height of the slice, dy. And we can just calculate that integral. We have to integrate y squared from 0 to h. So that gives me y to the 3 over 3 between 0 and h. So that gives me h cubed over 3 for the integral. So I get a third AH as the answer. So it's a nifty little calculation using calculus for the volume of a pyramid. But a mathematician like Gauss looked at this and was upset by it, because it would be nice to have a finite way of calculating this volume, maybe by decomposing the pyramid into finitely many pieces. And this is the same thing that bothered Hilbert, which now we can state his problem more precisely. If two three-dimensional polyhedra P and P prime have the same volume, is P necessarily scissors congruent to P prime? So if they have the same volume, can you chop one up into finitely many pieces and rearrange it to form the other? You can do that in 2 dimensions, as we proved. The question is, can you do that in 3 dimensions? So Hilbert thought the answer was no. And the reason being that if it were true, then it would allow us to give a finite definition of the volume of a polyhedron. And that went against his intuition, which was a very good intuition since he was David Hilbert. So, for example, one way of defining the volume would then just to be that the volume would, of a 3-dimensional polyhedron would, by definition, be the scissors congruence class of that polyhedron, the equivalence class of that polyhedron under the equivalence relation given by scissors congruence. And indeed, this is the way that if you look in motivic integration and so on in modern maths, this is a way that people do define some integrals. You define it to be some equivalence classes. So it's a way of doing integration without ever doing an actual integral. Yeah. So a few months after Hilbert stated the problems, I think this might have been the first Hilbert problem to be solved, because his student Max Dane solved this problem. But of course, someone had already done it before, namely the Polish mathematician Ludwig Birkenmeier had proposed and solved this exact problem back in 1882. That's how mathematics always goes. The founder of the person who the theorem is named after was never the person who proved it originally. So here's Dane's theorem. Well, one part of his theorem, the cube and the regular tetrahedron having the same volume are not scissors congruent. So here's a cube, and here's a regular tetrahedron. Regular tetrahedron means all the lengths are the same. And we choose these lengths in such a way that the volume of the tetrahedron is the same as the volume of the cube. But Dane showed that they are not scissors congruent. So although they have the same volume, you can't chop up the cube into finitely many pieces and rearrange it to obtain the tetrahedron. So how are we going to prove this? The way that Dane did it is that he introduced, which in modern terminology we call the Dane invariant of a polyhedron. So given a polyhedron P, we're going to calculate a certain quantity, which we're going to call D of P. And by definition, it's the sum over all the edges of the polyhedron of the length of that edge, funny symbol, with the dihedral angle of that edge over pi. So let me try and explain some of these terms. So this here is the length of the edge. It's just a real number. This here is the dihedral angle at the edge E. So if you have a polyhedron, that means you have a bunch of planes meeting at edges. And at each edge, you can take this interior angle formed by the planes. And we call that the interior dihedral angle at that edge. So for example, here's a tetrahedron here. The dihedral angle at E is this angle here, theta E. So that's going to be a certain angle, and it's going to be an angle between 0 and pi, and we divide it by pi. Okay, now where does this quantity live? And this quantity lives in a certain abelian group, namely the tensor product of the abelian group R with the abelian group R mod Z. Now, the reason why I chose this talk is because this gives you an introduction into abelian groups if you haven't seen them before. So let's try and explain this. This thing on the left is an abelian group. What does that mean? Well, some of you have seen the concept of a group before. A group is a set equipped with a multiplication operation, which is associative. There's an identity element, and every element has an inverse. Okay, so we think of groups as being like the group of symmetries of a certain structure. The set of all symmetries of a geometric structure would form a group, because you can compose symmetries together. When we talk about an abelian group, we mean that the multiplication operation is commutative. So in the group, we'll write the operation of multiplying two elements. We'll write it as plus, just because that's our intuition for commutative operations. So what I'm saying is that in this group, if you've got an element x and an element y, and you compose them together, which I'll write as x plus y, then x plus y must be the same as y plus x. Okay, that's what an abelian group is. This guy here is also an abelian group, and it's given by a quotient of two groups. The abelian group R, which is all real numbers under addition of real numbers, and the abelian group Z, which is all integers with group operation being addition. So here we take this set and we quotient it out by this group action of Z. So I'm not going to write it down formally, but I just want to give you some examples. What this means is that we're going to write a little symbol around each element now to say that elements inside R mod Z are identified by equivalence classes of real numbers. So if x is a real number, the equivalence class of x is the same as the equivalence class of x plus n, where n is some integer. So for example, the equivalence class of 1.4, which is an element of this group, is the same as the equivalence class of 0.4, which is the same as the equivalence class of 5.4. All of these things differ by integers. Okay, what is the group operation? The equivalence class of x plus the equivalence class of y is defined to be the equivalence class of x plus y. Okay, any questions on that? Because now I suddenly changed gears a little bit and I started doing some abstract maths.
Bruce,
Yeah.
reminds me of the floor function.
Yes, indeed. Especially the notation.
Yeah.
Yeah. So this is the tensor product of abelian groups, this thing over here. And what do we mean by the tensor product of abelian groups? So it's not something that you'd usually do in a third year course in algebra. You don't normally define the tensor product of abelian groups. So let me define it here for you. So let G and H be abelian groups. We define their tensor product as follows. It's the set of all finite sums, so formal finite sums of this form. So an element in G and then a funny symbol which we call tensor product with an element in H. And you have a sum of such things. So it could be G1 tensor H1 plus G2 tensor H2 plus dot 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 plus Gn tensor Hn. That could be an element of this set. But then we impose the following relations, namely that G1 plus G2 tensor H is the same as G1 tensor H plus G2 tensor H. And also G tensor H1 plus H2 is the same as G tensor H1 plus G tensor H2. Okay, so it's a set of abstract sums of abstract symbols quotiented out by these relations. Okay, that's quite an abstract definition, so let's try and make it more concrete. So what is a typical element of this group R tensor R mod Z on the right-hand side, where the Dane invariant is going to live? So for example, you could have 1.78 tensor the equivalence class of a quarter. Or you could have root 2 tensor the equivalence class of 1.398. Just remember the things on the left are real numbers, and the things on the right is any real number, but then you put an equivalence class symbol around it to indicate that that real number is considered equivalent to another real number if you can get from the one to the other by adding an integer. So for example, we can perform the following manipulations. 1.1 tensor the equivalence class of 0.2 inside this group is the same as 0.8 tensor the equivalence class of 0.2 plus 0.3 tensor the equivalence class of 0.2. Because remember, I'm using this rule here. This relation that G1 plus G2 tensor H is the same as G1 tensor H plus G2 tensor H. So I'm applying that relation here. Because 0.8 plus 0.3 will give me 1.1. And similarly, I could notice that 0.2, its equivalence class is the same as the equivalence class of 1.2, because these two numbers differ by an integer. So these are the kind of manipulations we're allowed to do inside this abelian group. One important thing to note here is that for any real number x and any rational number p over q, inside this abelian group, R tensor R mod z, we have that x tensor the equivalence class of p over q. Well, if you look at the way you can manipulate these things, you can take that over q essentially outside and then put it back into the x. So it's the same as x over q tensored with the equivalence class of p. And the equivalence class of an integer is 0, because any integer is equivalent to the 0 element of R, because it's an integer distance away from 0. So that is the proof that any real number tensored with the equivalence class of p over q is 0 inside this Dane group, where the Dane invariants live. So that tells us, for example, that if the dihedral angles are rational multiples of pi, then the Dane invariant is immediately going to be 0. At least that, that edge will contribute 0 to the Dane invariant. Okay, so yeah, you might have been lost a little bit there, but stay with me. So more precisely, Dane's theorem is as follows. Firstly, if P and P prime are scissors congruent polyhedra inside R3, then the Dane invariant of P is equal to the Dane invariant of P prime. So that's why we call it an invariant, because it's invariant under scissors congruence. If P is scissors congruent to P prime, then the Dane invariant of P is equal to the Dane invariant of P prime. Just like the volume, right? If P is scissors congruent to P prime, then the volume of P is equal to the volume of P prime. By the same argument as before, because you're just chopping it up into finitely many pieces, and volume is additive. Okay, so we've now found another invariant besides the volume. We found a Dane invariant, a more subtle invariant. And then part B is that if C is a cube and T is a regular tetrahedron, then the Dane invariant of the cube is 0, but the Dane invariant of the regular tetrahedron is non-zero. So this then establishes that it's not true that if two polyhedra in R3 have the same volume, then they are scissors congruent, because C and T have the same volume, but they're not scissors congruent because they have different Dane invariants. So let's prove this theorem. So part A, if you subdivide a polyhedron, that means you're going to be making a finite number of planar cuts. You're going to intersect your polyhedron with a plane and chop it up into two pieces that way, and so on. So here's a picture. Okay, I've got a polyhedron P at the top left, over here, and then I make a planar cut along this plane here. Okay, and that's ultimately going to result in splitting P into two pieces, P1 and P2. Now let's see what happens to the Dane invariant. The Dane invariant of P is by definition the sum over the edges of P. For each edge, I must take the length of that edge, tensor it with the dihedral angle over pi. Okay. Now let's have a look at what happens when we make this cut. We're going to introduce a bunch of new edges inside the cut polyhedra P1 and P2. So for example, this edge E is going to become E1 and E2 inside the cut polyhedra P1 and P2. But something that you immediately see is that the dihedral angle θ1 plus the dihedral angle θ2 must add up to pi, because over here we've cut a plane or an angle into two. So this was 180 degrees here, and we've just cut it up into two pieces. So this angle plus this angle must equal 180 degrees. But that means that as far as how the Dane invariant will change, the Dane invariant of P will change by, as far as this edge goes, I'm going to be adding the length of E1 tensor this dihedral angle θ1 over pi, plus the length of E2 times dihedral angle θ2 over pi, as far as the contribution of this new edge E is concerned. And these I can combine together to get the length of E1 tensored with θ1 plus θ2 over pi. And θ1 plus θ2 is pi. So this guy here is exactly 1, and the equivalence class of 1 is 0. So that contribution is 0. So the Dane invariant won't change at all along any of these new edges. So our conclusion is that the Dane invariant of P is equal to the Dane invariant of P1 plus the Dane invariant of P2. This shows that if two polyhedra are scissors congruent, then their Dane invariants are the same. Because this guy here is scissors congruent to P1 and P2, and they have the same Dane invariants. And any scissors congruence is just made up from a finite number of cuts. Okay, now let's have a look. So remember what the theorem said. Part B of the theorem was, it said that the Dane invariant of a cube was 0, but the Dane invariant of a tetrahedron was non-zero. So let's go ahead and calculate. What's the Dane invariant of a cube? Well, all the dihedral...
Sorry, Bruce, a bit.
Yes. Hi, Zaganya.
On the proof of A, what happened to length of edge E2?
Because this part of the tensor product was 0, it immediately made the entire tensor product 0.
No, okay. In the line above.
Okay, that's a very well spotted in Zaganya. I have made a mistake there. I thought I could shortcut that calculation, but I can't.
I think you can.
Oh, wait, hold on.
E1 and E2 have the same length.
They have the same length. They have the same length. That's right. Because E1 is equal to E2. I mean, E1 is this edge and E2 is this edge, but they have the same length, which is the length of the original edge.
Yeah, sure.
Maybe I should have written L subscript E, then you would have been happier.
Yeah, it's okay. Thank you.
Thank you. So all the dihedral angles in a cube are pi over 2. So that's a rational multiple of pi. So the Dane invariant is going to be 0. What about for a regular tetrahedron? Well, you can go ahead and calculate. So yeah, all the lengths are equal of all the edges. And so you can go ahead and calculate this dihedral angle here. Obviously, all these angles are going to be the same. And it's a nice little calculation you can do with cross products. And you can compute that this angle here is arc cos of 1/3. Which is this number here. And the question is it a rational multiple of pi or not? Okay, so that means the Dane invariant of the tetrahedron is 6 times the side length L tensored with this angle over pi. And you can go ahead and check that this number is irrational using some trig identities. I challenge you to do that. To prove that arc cos of 1/3 is irrational. So this shows that this number is non-zero.
Sorry, is it a property that the tensor product can only be zero if one of the things being producted is zero? Because it seems like we're kind of implicitly using that fact.
Yes, if one of the things is irrational, then the tensor product isn't zero. Yes, we are using that, but you can prove that by writing down a homomorphism from this group into R, non-zero homomorphism. Yeah. So, in fact, more is true. Sidler proved in 1965, let P and P prime be three-dimensional Euclidean polyhedra, then P is scissors congruent to P prime if and only if they have the same volume and the same Dane invariant. So up to now, we proved that the forwards direction, right? We proved that if P is scissors congruent to P prime, then they have the same volume and the same Dane invariant. Having the same volume is clear, and having the same Dane invariant is what we just proved. And the question is, of course, what about the reverse implication? So are these two invariants, volume and Dane invariant, sufficient to identify the scissors congruence class? And that is true. Okay, and this is quite a hard theorem. And there's a nice modern proof of this using homological algebra. And it amounts to the following statement. So those of you who know a little bit of abstract maths, I'm just throwing this out there for you. You need to compute the second group homology of the group SO3 with coefficients in R3. And it turns out that this statement is equivalent to saying that this second group homology is zero. And yeah, there are tools to compute this second group homology. It's still quite a long calculation, but at least it can be phrased in this more invariant way. Okay, I want to explain why, just at the end, why how I'm interested in this. I mean, I think it's a beautiful thing in its own right, but it did sort of impact into the research areas that I work on, and I want to explain a little bit about that. So in 1968, the physicists Ponzano and Reggi were studying a model for three-dimensional quantum gravity. The building blocks for their model...
Sorry
a
bit, Bruce, on this theorem of this.
Yes.
We proved the last theorem, but it seems it is contradicting with this theorem.
No. Part A of this theorem says that if they're scissors congruent, then they have the same Dane invariant.
Yeah, I mean for part B.
So this part B shows that they are not scissors congruent.
Yeah, like this part B is, I'm thinking like is a converse of part A.
No, part B does use part A, that's right, but part B simply calculates that the Dane invariant of the cube is zero and that the Dane invariant of the tetrahedron is non-zero. And then by part A, we can conclude that the cube is not scissors congruent to the tetrahedron.
Yes.
I just write that down, but because it's implicit in the statement.
Yeah, but now on this theorem of this guy of 1965.
Yeah.
Now it's confusing because you say that P if is Caesar congruent to P prime, then then invariants are going to be equal.
Yes.
And is if and don't know if how is it no contradiction with that counter example?
It's not, because in this example the Dane invariants were not the same.
Yes.
All I'm saying is that if the Dane invariants are the same and the volumes are the same, then they will be scissors congruent. But yeah, the Dane invariants are not the same. So
Oh, okay. Now,
yeah.
I understand. Yeah.
Okay. So yeah, the physicists Ponzano and Reggi were studying a model for three-dimensional quantum gravity, and the building blocks for their model were the 6J symbols, which are certain real numbers which arise from the representation theory of SU2. So this is stuff that I'm interested in. It falls under mathematical physics and topology. And Zaganya, who was just speaking now, is my PhD student, and he's working on this. And Hasana, my other PhD student, is also working on 6J symbols. So they showed that asymptotically, the 6J symbols have to do with the geometry of Euclidean tetrahedra. Okay, that is quite interesting. And they actually found symmetries of the 6J symbols. And when they translated this to what happens at the level of the tetrahedra, they showed that these symmetries of the 6J symbols geometrically correspond to transforming the lengths of a tetrahedron in a certain way. So here I've got a tetrahedron. It doesn't have to be a regular tetrahedron. All these lengths could be different. And I choose a pair of opposite edges, A and D. And then I define S to be half the sum of the remaining edges. And then I make a new tetrahedron with new lengths, A prime, B prime, C prime, D prime, E prime, and F prime, given by this formula here. I leave the lengths of A and D the same, but I change the lengths of B prime, C prime, E prime, and F prime. Okay, so I form a new tetrahedron with different lengths. And Roberts noticed that it's a consequence of the calculations that Ponzano and Reggi do in their paper, that the volume of these two tetrahedrons are the same. They knew that, but they didn't. They were physicists, so they didn't really think about Dane invariance. But it's also a consequence of the calculations they did, that the Dane invariant of T is the same as the Dane invariant of T prime. So by the Sidler's theorem, that means that T is scissors congruent to T prime, even though it's a completely different tetrahedron. So this allows us to conclude that a generic tetrahedron T gives rise to 12 different scissors congruent, but not congruent tetrahedra T prime. The number 12 there is because you can apply this Reggi symmetry in all the different ways. You can choose two pairs of opposite edges, and then you can also compose them. So you end up getting 12 distinct symmetries. So yeah, so arising out of some work in mathematical physics, they ended up coming up with, from a given tetrahedron, you can actually calculate 12 different ones, which are scissors congruent to your original one, meaning you can chop up T into finitely many pieces to form T prime, even though T prime manifestly has different lengths from T, so it's not congruent to T. So that's my research area is kind of in that direction, and that's how I was sort of interested in this Hilbert's third problem. Yeah, I thank you for listening to me.